We've already talked about light having wave-like properties, and the waves that we're familiar with in our everyday life we consider to be disturbances traveling through a medium. We talked about dropping a pebble in water, and the water is the medium, and we see the wave travel outwards. We think about sound waves, which is a disturbance in the air. We think about a wave traveling through this rope. The medium there is the rope. So in the mid-19th century, it was completely reasonable for folks to say, well, look, light has wave-like properties. It must be a disturbance traveling through a medium. And they said, well, what do we call that medium, even though we don't observe it directly? Well, let's call it the luminiferous ether. So an obvious question that was facing folks who had this reasonable assumption, they said, well, can we somehow detect the luminiferous ether? Can we validate the luminiferous ether existing? And a key realization is well, we must be moving quite rapidly relative to the luminiferous ether. How do we know that? Well, we just have to remind ourselves that obviously the Earth is rotating, but not only is it rotating on its own axis, but it's rotating around the sun. And so if this is the sun right over here, this is the Earth. The Earth is rotating, and these are all rough figures. The Earth is moving around the sun at approximately 30 kilometers per second. 30 kilometers per second. By our everyday standards, that's quite fast, but we're not done yet, because the sun is also moving around the center of the galaxy. And this isn't an actual picture of the Milky Way. Obviously, we haven't gotten this far from our own galaxy to actually get this type of a vantage point. But if the sun were right over there, the sun, estimates are moving with a speed of roughly 200 let me write that in a better color so you can actually see it. 200 kilometers per second. 200 kilometers per second around the center of the Milky Way. And then the Milky Way itself could be moving. So we don't know our actual our orientation relative to the ether, but we're constantly changing our orientation. We're moving in these orbital patterns. If there is some type of luminiferous ether, and I'm just going to draw these lines over here to kind of show our luminiferous ether, we must be moving relative to it if we orient ourselves just the right way. In fact, the odds of us being stationary relative to the ether are pretty close to zero, especially if we wait a little. If we're stationary relative to the ether right now, let's say at this point, since we're changing our direction, we're not going to be stationary relative to the ether at that point. And that's just when you consider the Earth's orbit around the sun. It's even more true when you think about the solar system's orbit around the center of the galaxy, or even the movement of the galaxy. So we should be moving relative to the ether, or the ether should be moving relative to us. So we should be able to detect some type of what's called an ether wind, because it should be moving relative ether wind. Now, how would you detect an ether wind? Well, let's think about some other type of medium moving relative to us. Let's say that we are sitting on an island. Let me do this in a better color for an island. So let's say that we're in an island that's in the middle of a stream. So these are the shores of the stream. And there is some type of a current. So the water is moving in that direction. So that's the medium. And now let's start a wave propagating through this. So if I were to just take a pebble and drop it right over here, what would happen? Well, the wave is going to propagate faster to the left than it is to the right. And this is from our everyday experience, and that's because to the left, it's moving, the medium is also moving to the left. So as the medium moves and then you propagate through that medium, you're going to move faster to the left than to the right. So the wave is going to propagate something. So after a small period of time, the crest on the right might be there, but the crest on the left might be there. So it might look something like this. And then after another period of time, it'll look something like this. So the general point is, for this little stream example, you're going to see your wave propagate faster in the direction of which the medium is moving. So similarly, if you have an ether wind, and and this luminiferous ether is the medium by which the light propagates. The light is a disturbance in this medium. Then if this ether wind has some, let's say it has some speed, well, let's just call it s. If you were to try to propagate light in that direction versus in this direction, versus in that direction, it should go faster. We should notice it going faster if it's going along the same direction as the ether, because it's propagating through something that's also moving relative to us. And likewise, if it's going in the opposite direction of the ether, even though it's propagating through the actual ether at that same speed, the ether is moving in the other direction. So the light, based on our 19th century understanding of the universe, the light should seem slower. So you can imagine people started to theorize, well, maybe we can measure light in different directions and see if relative to us, we see a different velocity for light. Now, the problem is that in the mid-19th century, light is incredibly fast. We now know that the speed of light is approximately 300,000 kilometers per second. And in the mid-19th century, we didn't have good tools to measure this with a lot of accuracy. Especially because the ether wind itself, even if you say, hey, this is 30 kilometers per second, maybe we're moving around the galaxy at 200 kilometers per second, maybe 300 kilometers per second, that's still a small fraction of the actual speed of light. So if you don't have a lot of accuracy when you're measuring the speed of light in these different directions, and the ether wind is so slow relative to the speed of light, well, with just traditional tools in the 19th century, you're not going to be able to detect this actual ether wind if it existed. And that's what gets us to the famous Michelson-Morley experiment, because there they didn't just directly try to measure the speed of light in one direction or another. Instead, they thought about, well, let's split some light into two different directions and then recombine them and see the interference patterns. And if the different directions traveled at different speeds, then we'll have different interference patterns. And we're going to see that in the next video.